So for the last lesson of this vectors unit, we are going to be discussing more vector applications. So the first thing we're going to look at is vector projections. So in this case, with vector projections, that is when you're given two vectors like v and w, and you're going to create a third vector as that projection of v onto w. So it's denoted as proj sub w of v. And so what this means is that vector projection is that we're going to take v and we're going to project it on to w, which means it's going to go in the same direction as w. So what we're going to find is we are going to find essentially two separate vectors. So we're going to have, first of all, w1, which is that change of v when it is projected onto w, which means that it has been moved to be in the same direction. And then w2 is essentially the perpendicular movement of the tail of vector v in order to move it. So figure 1 here shows what happens when theta is acute. And then figure 2, it shows what happens when theta is obtuse. So in both of these, you're going to get a right triangle, but when theta is acute, it's going to go down on top of vector w and usually extend out further. But when theta is obtuse, v is going to pretty much create opposite rays with the with vector w. So they should create a straight line. So that vector projection formula of v onto w is the projection, or the proj, sub w of v. So the projection of vector v onto w equals v times w over the magnitude of w squared times w. So now we are going to go ahead and find the vector projection of v onto w. So here we have vector v at -4, -8, and w at 3, 1. So we're going to go ahead and find that projection. So the projection of vector v onto w. And that is going to be, well, first I'm going to find that dot product of the vectors. So I'm going to have -4 times 3, that is -12. And then -8 times 1, that is a -8. And then on the denominator, we are going to be finding the square root of 3 squared plus 1 squared, and then that is squared, so it kind of cancels out these roots. So on the top, I have, actually I need to bring in my w, because this is all multiplied times vector w of 3, 1. And so then I'm going to go ahead and simplify. So I have -20 And then 3 squared and 1 squared is 10. The square root of 10 squared, though, is still 10. And then that is multiplied times 3, 1. So negative 20 divided by 10 is a negative 2. So I have negative 2 as a scalar of 3, 1. And so we will multiply this, and it will get us negative 6, negative 2. So this is our projected vector v. And what this tells us is that, well, honestly, the scalar tells us more than anything. So
that's just a little.
The scalar tells us that, well, first of all, the magnitude was changed. Is 2 times as long. And the direction is reversed because of that negative. So this vector probably looks more like figure 2. All right, so let's go ahead and look at example 2. So both of these vectors are in linear combination, so we need to change them to component form. So we need v as 6, 3, and then w as 2, negative 3, and then we are going to get the projection of w onto v, or v onto w. So we're going to get that dot product first. So we're going to have to multiply the a's together. So 6 times 2 is 12. And then 3 times negative 3 is negative 9. And then we're going to take the square root. Need to make a bigger parenthesis of, let's see, 2 squared plus negative 3 squared. That is squared. And then we've got to multiply it times 2, negative 3, because that is our w. So then we're going to start simplifying. So we have, let's see, 12 plus negative 9 is 3. And then I have, let's see, 2 squared plus negative 3 squared. That gives me 13. So we have 3 over 13 times 2, negative 3. And so that is going to give us 6, 13, and negative 9, 13. So that is our projected vector. So now we are going to look at writing these projections as a sum of orthogonal vectors. So by vector addition, we can also write vector v as the sum of vectors w1, and that is that projection vector that we just found. And then we have that vertical vector of w2. So vector v should be equal to w1 plus w2. So this creates orthogonal vectors that do give us pretty much like the legs of the right triangle for what we have as that horizontal and vertical for vector v. So let's go ahead and find the orthogonal vectors that are there for v and w. So remember, w1 is going to be equal to the projection of v onto w. So we have to find the dot product. So let's see, 2 times 3 is 6, and then 6 times 3 is 18, and that is over the square root of 3 squared plus 3 squared, which is 24, over 18. Oh, and we need to put in the w. And so that is going to be 24 over 18 times 3, which this reduces to 4 over 3 times 3. And so w1 is actually equal to 4 when you multiply by that scalar. So then remember that vector v is equal to w1 plus w2. Well, we just found what w1 should be. So we are going to take vector v, which is 2, 6, and it should equal 4 plus w2. Now we know that we can subtract 4. So we could use our algebra. And we have that 2, 6 should minus 4 equals w2. And so when we do that subtraction, we should get the w2 is negative 2. So now that we know w1 and w2, we can write vector v as a sum of 2 orthogonal vectors. So that should be 4 plus negative 2, because we found w1 by using our vector projection, and then we use subtraction to find vector 2, or w2. So, and remember, vectors are orthogonal if their dot product is equal to 0. So that's one thing that we can check really quick, because, let's see, well, w1 times w2 is, let's see, 4 times negative 2 is negative 8. And then 4 times 2 is 8. That equals 0. So they are orthogonal. So let's go ahead and try this with number 4. So we have that vector v is 2j, so these are linear combinations, and w is 8i minus 6j. So v is going to be 0, 2. W is 8, negative 6. And then to find W1, that is the projection of V onto W. So we have that dot product. And so that is going to be 0 times 8, which is 0, plus 2 times -6, which is -12. That is over the square root of W squared. So that is going to be 8 squared plus -6 squared. And then that is all squared. And then that is times 8 -6. So that leaves us with -12 over, see, 8 squared is 64, -6 squared is 36. That's over 100. And then we have 8 -6. So that is going to reduce to, let's see, -3 over 25 times 8 -6, which will give us, let's see, -24 over 25 times, let's see, and then 18 over 25. So that is W1. And then we are going to use that to find that pretty much our W2. So we know that V is 0, 2. And actually we can just go straight to like W2 equals W1 or V minus W1. So W2, we have V, which is 0, 2. We're going to subtract W1, which is -24 over 25, and then 18 over 25. So that is going to give you 24 over 25, and then 2 minus that 18 over 25, that's going to be 32 over 25. So to write this as a sum of orthogonal vectors, you are going to have V equals W1, which is -24 over 25, and then 18 over 25. And then we have 24 over 25 and 32 over 25. So for force applications, we're going to start off with kind of an example, and we're going to talk through some things before we really just jump into another example. But force is always figuring out what force is needed to keep something from moving or to maybe start something moving. So in this case, we have a rock on a hill. This is kind of the easiest thing to kind of really think about. And so we have a 400-pound rock on a hill with a 30-degree incline. So F, vector F, represents the force exerted by the rock due to gravity. So remember, gravity like pulls straight down no matter where you are. And V is the vector of the incline. So V is right here. And so it represents kind of the direction of the hill. And W1 is the projection of F onto V. So it's what happened when we put F onto V. And the magnitude of W1 is the force required to keep the rock from rolling down the hill. So let's talk about a couple of things before we really jump deep into this. So, let's see. Let me find a little bit of room. So if we were just on flat ground, then vector F would still be pulling straight down. If we had our rock, our 400-pound rock, and then vector V is now 0 degrees. And so how much force would it actually take to stop this 400-pound rock? Well, it actually would take 0, because it's only getting pulled down. There's no incline. So it would stay where it needs to be. Then if you reverse that situation and instead you had a 90-degree incline for V, you still had the 400-pound rock, but now gravity is pulling right with it. So how many pounds of force is it going to take to keep this from going anywhere? Well, it's going to take all of it. So if you were a person trying to stop it, you would need 400 pounds of force to stop the rock and hold it in place. So you're always going to be somewhere between 0 and the weight of the object that you need. So we have a 4-step process for figuring this out. And if you kind of go through this process every time, it really helps you figure out where you need to be. So we're going to write F as a vector first, okay? So vector F is going to represent, remember, the force of gravity. So gravity doesn't move to the left or right. It's not going to move the rock to the left or right. So that is going to be 0. And then gravity is always pulling down towards the center of the earth. So that is going to be a negative 400, since that rock is 400 pounds. So then for step 2, we are going to write vector V as a unit vector in the direction of the hill. So remember that a unit vector always has our has a magnitude of 1. So we're going to start out with trig form. So we have 1 times, and then our angle is 30 degrees. So we're going to have the cosine of 30. And then we're going to have 1 times the sine 30. So if we look at our unit circle, then we can get our values for cosine and sine. So this gives us the square root of 3 over 2 and 1/2 as our unit vector. So now we are going to find W1 as a projection of F onto V. So for that projection formula, this is the same thing as the projection formula that we used earlier in the lesson. We have just taken this and changed it to F and V. So it's still the dot product of the two vectors, and it is still the magnitude of the vector that you're being projected onto. So just we are projecting onto V. So we're taking F and putting it on V. So we have another thing to remember, and that the magnitude of V squared is going to equal 1, since V is a unit vector and its magnitude is 1. So in some ways you can almost drop your denominator. So we're going to take that dot product, and so we are going to have 0 times the square root of 3 over 2 plus 1/2 times negative 400. And then this is going to get projected onto vector v. So 0 times the square root of 3 over 2 is 0, and then 1/2 of negative 400 is a negative 200. So we have negative 200 v. And so now we are going to go ahead and find the magnitude of W1. So notice I'm not plugging in vector v because that is just the square root of 3 over 2 and 1/2. But if we did go ahead and plug in vector v, what we would have is that negative 200 cosine 30, and then negative 200 sine 30. And then when we went and we tried to find the magnitude of it, which this is W1, and so what would happen is we would have the square root of 200 cosine 30 squared plus 200 sine 30 squared. And you would find that once you put this in your calculator, you would get 200 pounds, which is actually the absolute value of what you found earlier, because you had that 200 times v. And what you will find that as with regularity, that you will always have the absolute value of whatever that number is in that initial projection calculation, since you used a unit vector. So the magnitude of W1 is 200 pounds. So there are 200 pounds of force required to keep the rock from moving down the hill. So let's go ahead and look at number 5 and see if we can find the force required. So remember, if all else fails, you can always draw yourself a picture and see if it helps. So we have a 50-pound cart sits on a ramp with an incline of 60 degrees. What force is required to keep the cart from rolling down the ramp? So here is our ramp. Here is our cart. And so we have an incline of 60 degrees. And this cart is 150 pounds. So remember that vector F is that force that is pulling down. And then vector V should be your incline. Now remember, it doesn't matter how long or how short vector v actually is, because we are just projecting vector f onto vector v. So you have vector f, that's not going to the left or right, so you are pulling down at 150 pounds, so and it's 0 for the first component because you're not going to the left or right. So then v as a unit vector in trig form is going to be the cosine of 60 degrees and then the sine of 60 degrees. We can pull those values off of our unit circle and have 1/2 and then the square root of 3/2. So now we need to go ahead and find W1. So W1 is that projection of F onto V. And so we are going to have, see, is our dot product, which is 0 times 1/2 plus negative 150 times the square root of 3/2 and then vector V. And I'm not even going to bother putting in vector V because we're just going to need that number that is going to wind up being our scalar. So, and of course, that is over typically our magnitude, but our magnitude of vector V, since it was a unit vector, should be 1, so that would be 1 squared. And so it's actually just going to go away too. So we have 0 times 1/2 is 0. And then 150 times the square root of 3/2 is negative 75 square roots of 3. And this is multiplied times vector V. But then I am going to take the magnitude of W1, which we now know is 75 square roots of 3. I just need to make it positive because it's the absolute value. And remember, force cannot be negative. You can't exert negative force. And we can go ahead and leave this as is, or we can make it a decimal, and we would get 129.9 pounds of force. So let's go ahead and look at number 6. So we're getting closer to the end. These are going to start going a little bit faster. And so one thing I want you to make a note of is that a lot of these can be solved by using similar triangles in trigonometry if you remember that, but sometimes it's just a little bit easier to use the vector. So Carly is pulling her brother on a sled up a hill with a 12-degree incline. So I'm going to try to draw a straight line. And if the combined weight of the sled and her brother is 45 pounds, what force is required to keep the sled from sliding down the hill? So we have the sled with her brother on it. So that is 45 pounds. So vector F is 0, and of course it's negative 45 because gravity always pulls down. And then our unit vector, vector V, is the cosine of 12 and the sine of 12. And so these are going to not be on your unit circle, but that is fine because we can go ahead and just use them as they are and then put them into our calculator when we find our dot product. So let's go ahead and find W1, which is the projection of vector F onto vector V. And so we really just need that dot product. So that's going to be 0 times the cosine of 12 plus negative 45 times the sine of 12. And that is all multiplied times vector V. So the 0 times the cosine of 12, that is going to go away. And then the negative 45 times the sine of 12 is what we can put in our calculator. And we should get negative 9.36 V. So to find that magnitude of W1, remember you can drop the cosine 12 and the sine 12 off of this, because you should just get the positive version of what you got off of your projection. So that's a positive 9.36 pounds. Okay, so let's talk about some work applications here. So this is just another application of vector projections. So your work done W by a constant force F acting on the line of motion is the magnitude of the force times the distance traveled. So your work is the constant force, so that could be represented by vector F here. So we'll just use the magnitude of F, because you can find that by finding the force. So that would later be the projection of F onto AB. And then you would multiply it times the distance traveled, which the distance traveled would be point A to point B. So that would be the magnitude of AB. So just a quick note, work is measured in foot-pounds in the customary system. So whenever we find the amount of work that it takes, we'll use foot-pounds if we are using like feet, yards, pounds, things like that. And then it is measured in joules in the metric system. So anytime we're using grams, meters, liters, things like that, then we will need to use joules. So first, we're going to determine the work done by pushing a 500-pound crate 12 feet. So remember that the amount of work is equal to the magnitude of the force vector times the distance traveled. So that would be AB. So in this case, we need 500 pounds. That's the magnitude of our force. And then that is going to be times 12. So that gives us 6,000 foot-pounds of work. So for number 8, we need to determine the work done by a crane lifting a 2,300 pound car 5 feet. So we are going to have the work of the magnitude of the force, which would be 2,300, and then the distance traveled, which is 5 feet. So that's 2,300 times 5, which is 11,500 foot-pounds. So if your constant force of F is not acting along the line of motion, then the work done is given in either of these two forms to account for the fact that the force is going to be different if it's not going straight across in the same direction as AB. So you will have your projection form, which is W is the magnitude of the projection of F onto AB. So essentially we move that vector like we have been, and then it'll be times the magnitude of AB. And then your dot product form is F times AB which also works. So let's go ahead and look at number 9 and look at what happens when our force is not going in the same direction as AB. So we have that a man pushes a car 8 meters with a constant force of 140 newtons at a constant angle of 50 degrees. So we need to use that projection formula to find the work done. So for this, we are actually going to use some of our right triangle trig and our vectors. So what's going to happen is, let's go ahead and like draw a picture. So we have our car. Sorry, that's a terrible looking car. Actually here, I'm just going to make it a box. So we have our car, and we are going to pull the car with 140 newtons. And it's going 8 meters. And so it's not being pulled straight up. It's being pulled at an angle of 50 degrees. So we are going to actually use that right triangle trig. So we are going to have, cosine, it's at 50 degrees. And remember, cosine is adjacent over hypotenuse, okay? So we know that the magnitude, because we're going to essentially use, cosine theta is the projection, the magnitude of the projection actually of AB and F over the magnitude of F. Okay, because that would be our projected length of F. So cosine, if we plug this in, so the cosine of 50 degrees is going to equal that projected magnitude of F on AB over 140. So if I look at this formula, I can actually get that vector projection by using that right triangle trig. And I can just multiply each side by 140. So that gives me 140 times the cosine of 50 equals the magnitude of the projection of AB and F. And that actually gets me 89.99 equals that projection. So then I have my magnitude of AB, which was 8. So I can find the work by taking 89.99 times 8, and that is 719.92. And that is going to be joules because we are going in meters. So let's go ahead and look at number 10. We're getting close to done. So we have, a force of 60 pounds exerted at an angle of 75 degrees above the horizontal is required to slide a sofa 20 feet across the floor. We're going to use the dot product formula to find the work done. So in this case, we are going to take, our work is our force times vector AB. So our force vector is going to be that 60 pounds. So that's the magnitude. times the cosine of 75 degrees, and then 60 times the sine of 75 degrees. So we're pretty much just writing that vector in trig form. And then we're going to multiply it times AB, which is 20 feet across the floor, so that is horizontal. We don't know if we're going to the left or right, so we will just assume the positive since we can't have negative work anyway. So we are going to use our dot product. And so we will have, let's see, 60 cosine 75 times 20 plus 60 sine 75 times 0. So that is, see, 60 cosine 75 times 20 is 310.58. The other term gets you 0, so it just goes away. And so this is foot-pounds, since we are using customary measurements. All right, and then number 11. Rick is pushing a snowblower with a force of 90 pounds. The handle of the snowblower makes a 60-degree angle with the ground. So how much work does it do if he pushes the snowblower 15 feet? So we're going to go ahead and just use that dot product again. So we have force times AB. So that is going to be, see, it is, he's pushing with a force of 90 pounds. So that is our magnitude. And then we have, let's see, an angle of 60 degrees. So the cosine of 60. And then 90 times the sine of 60. And then AB, he is pushing it 15 feet. So that is going to be 15. He's pushing it, so it's going to go horizontally. So it's 15, 0. So then we're going to use that dot product and have 90 times the cosine of 60 times 15 plus 90 times the sine of 60 times 0. So that 0 is going to take out that entire term. So 90 times the cosine of 60 times 15 gives us 675 foot-pounds of work.